Okay, I think this is the last video of my series videos for my final project. Of course, in this video, we will discuss the time complexity for the application. We will analyze each algorithm one by one and consider them as a whole. So let's analyze the fourth main algorithm. The first algorithm is partitioning monotone polygon, and its time complexity we know in class is big O n log n. And the second algorithm is the triangulation, and also we know it's big O n. So these two steps are already being proved in the class, so I will only dig into more deeply. And the third algorithm is doing breadth search in a dual graph, and this involves two parts. The first one is converting those triangles after the triangulation into a dual graph. And then we can apply breadth search in the dual graph. And these two steps are both linear, which is big O n. And the last step is the final algorithm. It also involves two parts. The first one is find left and right vertices, and the second one is to apply the final algorithm itself. We'll talk about an example for this step. Both steps are also linear, which is big O n. So for the rest of the video, I will mainly talk about third and fourth algorithm. I will discuss their time complexity. Let's talk about the third algorithm, run breadth search in a dual graph, analysis its time complexity. We will see why it's linear. So first consider, given n vertices of a polygon, how many triangles we will have after the triangulation? Yes, we have exactly n minus 2 triangles, and we have this conclusion in the class. So with this information, let's consider how many vertices of the dual graph we will have after converting those triangles into a dual graph. The answer is very simple. The number of triangles equals the number of vertices in the dual graph. The reason is also very easy. Let's consider this example, this very familiar example. We have three triangles after triangulation, and so we have four vertices after converting those triangles into a dual graph, because each vertex represents a triangle. So how many triangles we have and how many vertices we will have in a dual graph. And this is about the number of vertices. But how about the number of edges? It is still linear compared to the number of vertices? Well, the answer is yes. Also, let's look into this example and consider this vertex. How many edges it has? It has 1, 2, 3 edges incident to it. But can it have the fourth edge? The answer is no, because in this case, we only have triangles. In other words, a triangle, consider this triangle. It has at most 3 neighbors, this one, and this one. It cannot have the fourth neighbor. So in the case of the dual graph, a vertices has at most 3 neighbors, this one, and this one. As a result, it has up to 3 edges. So we can conclude the number of edges is bounded by big O n. In other words, the number of edges is 3 times n. N is the number of vertices. Consequently, we have the time complexity for the converting triangles into a dual graph, which is big O n plus big O 3 times n, which is big O n, which is linear. And with this conclusion, The time complexity of breadth search in a dual graph is so easy to conclude. As we know, in general speaking, the time complexity of a breadth search is big O n plus m, where n is the number of vertices and m is the number of edges. So with the conclusion and previously, the resultant time complexity for the whole step is big O n, which is linear. At this point, we proved the time complexity for the third algorithm, and we only have the last step. The final algorithm is time complexity to prove. But before we discussing the time complexity of the final algorithm itself, let's consider its pre-processing step. That is, define its left and right vertices. Recall in the previous example video, we talked about an example of final algorithm, this one, and we soon have those left and right vertices. So we define vertices on this chain are left vertices. Vertices on this chain are right vertices. So this information is given in advance, but for the purpose of discussing time complexity, we should clarify this. The way we determine type of each vertex is very simple. We walk along those portable lines, those dashed lines or internal diagonals, and determine the types of two endpoints of the same line. They are opposite. So, for example, consider dashed line MB, and we define the type of vertex B is a right vertex. So its opposite endpoint, which is M, its type is opposite to the type of B, which is left vertex. So we can only visit each portable line only once to determine types for all vertices. So the time complexity of finding left and right vertices is bounded by big O, capital N. Notice, capital N is the number of vertices of the triangles determined or after we're running the breadth search in the dual graph. In other words, capital N is less or equal to N, and N is the number of vertices of the original polygon. So we can conclude capital N is bounded by big O n. And with this information, we can step a little further. We run each vertex once to run the final algorithm. So we visit this vertex once and then to compute the shortest path or update our funnel. So the overall time complexity for the final algorithm is big O n plus big O capital N, which equals big O n overall for this step. At this point, we proved the time complexity for the final algorithm. It's time to summary. Well, the first step, we have big O nlogn for partitioning monotone polygon. And then we have big O n for triangulation. And the third step, we have big O n linear time for doing breadth search in a dual graph. And finally, we have big O n for the final algorithm. So we have big O nlogn, where n is the number of the original polygon for the whole application, which is a little bit surprising, right? Imagine we're doing all of these algorithms to compute the shortest path, but the time complexity is pretty fast, pretty efficient. It's just the time complexity compared to sorting a compare-based array, which is pretty fast, right? So I think it's time to conclude the series video of my final project. But for the last show, I will show the demo to find the shortest path in the maze, which is a single polygon, which is this case. So as you can see, this polygon is a maze and it's very special because every angle for this polygon is right angle, which is 90 degrees. So we will compute the shortest path from this green point, start point, to this right point, this end point. And notice we also have those dead end. So our algorithm, our application should avoid this to compute the shortest path. So let's do it in my Java implementation. Let's go to the command line and run the visualization program to show the result. Okay, as you can see, this is our maze. We will compute the shortest path from the start point to the end point, right point. So first step we will do is to partition monotone polygon. Let's do it. Okay, at this point, we partitioned monotone polygons. And then we will triangulate each monotone polygons. Let's do it. Okay, we have many triangles at this point. And then we will convert those triangles into a dual graph. So let's do it. Okay, as you can see, this green vertice and green edge are our dual graph. And at this point, we can run a breadth search in this dual graph to compute the shortest path with triangles in the dual graph. So let's do it. Okay, the path highlighted in blue is the shortest path in the dual graph. And finally, we feed the final algorithm with these triangles to compute the real shortest path. So let's do it. But first, let me go back to the original polygon to see the shortest path more clearly. So let's compute the shortest path. Okay, as you can see, the path highlighted in cyan are the paths we want. Okay, all straight lines, all the way to the endpoint. So at this point, we got our shortest path. And through this example, you can see the reason why we can apply this application, those algorithms to other fields, like game AI or Roblox. So imagine your robot want to go from this point to this point, and you can compute the path and let the robot move along the path. So also in a game, you want the character move from this, and you always want them to go along the shortest path. You can always use this application. So for the game Left 4 Dead, the zombies generated at a certain point, it goes along the shortest path to the endpoint, which is the place where the players. So we can compute the shortest path, and the zombies will go along the path, go straight to the players, which is amazing, right? So I think this is all of my presentation or the demo for my final project. I hope you have fun with my videos. So thank you for watching. Thank you.